The formation of lithium-rich giants has been an evolutionary puzzle for decades. Several mechanisms have been proposed to explain their existence, but it is not clear which mechanism or mechanisms are responsible. One proposed mode of lithium enhancement is rotationally induced mixing, which suggests these stars should be rapidly rotating. However, this is challenging to observe spectroscopically. The effects of macroturbulence can mask the expected signal of a few kilometers per second for evolved stars. The Kepler field hosts more than 100 lithium-rich giants. Because of their large radii, a few kilometer per second equatorial velocity would imply a rotation period of about 100 days. Variability on this timescale in Kepler data is typically removed by the Kepler pipeline in its attempt to clean the light curve of instrumental systematics. We've developed routines to re-reduce Kepler data specifically to preserve these slow signals. This enables us to find rotation periods even longer than 100 days, this one's about 120 days, in Kepler data, so we can explore the rotation distribution of these lithium-rich giants. To find out more, come check out my poster.
Hello, I'm Adam Finley, and I recently completed my PhD with Sean Matt at the University of Exeter in the UK, where he focused on modelling how stellar winds remove angular momentum from stars like the Sun. By using in-situ measurements of the solar wind, we can provide a valuable constraint for models that attempt to explain the rotation evolution of Sun-like stars, that is, the rate at which angular momentum is lost through the solar wind. We have explored data from Parkes Solar Probe and Solar Orbiter, and our main findings are that firstly, the solar wind angular momentum flux, although highly variable, is comparable with previous observations when we use sufficient averaging to remove local fluctuations. And secondly, there is a strong trend of angular momentum flux with solar wind speed, which has the fast wind typically carrying oppositely directed angular momentum to the slow wind. In future, we hope to be able to make multi-spacecraft observations of the solar wind angular momentum flux, along with measurements outside of the ecliptic plane using Solar Orbiter. I will upload this slide as a poster for you all to look at. Thank you for your time.
Hello everyone, I'm Shreya Shetty and my work is focused on understanding the internal nucleosynthesis inside asymptotic giant branch stars or AGP stars. For this purpose, we developed a new tool which disentangles the complex parameter space of AGP stars by using high-resolution data and the Gaia parallaxes. Later, by using the well-constrained stellar parameters, we located the AGB stars in the HR diagram and discovered some low-mass AGB stars. These are stars with Sun-like masses and Sun-like metallicities showing evidences of heavy elements production, which was unaccounted for by the TP-AGB models previously. We also then compared the chemical status of these AGB stars with their evolutionary status and found a very nice agreement between the heavy elements production in these stars and their evolutionary status or their location in the HR diagram.
Good afternoon, I'm Thomas Kranzer of the Leibniz Institute for Astrophysics in Potsdam, and I want to present you in this poster some long-term data on Betelgeuse. What you can see in green is the radial velocity data from our robotic 1.2 meter telescope Stella on Tenerife. In violet and red, you can see data from the bright photometric satellites. And for comparison, overplotted is the AAVSO Johnson V data in blue. What you immediately can see that the RV curve basically follows the photometry quite tightly, which is also true at the grand dimming event. But here you can see that the radial velocity lags roughly 30 days behind the photometric curve. You can also see that we have another dip here in December 2020, where we have also a very heavy infall event, which shows no sign whatsoever in photometry. If you want to see more, please visit.
With this project, we wanted to better understand why some red giants show magnetic activity. Thanks to a unique combination of asteroseismic analysis performed on 4,500 red giants observed by Kepler and complementary high-resolution spectroscopic data, we showed that there are three distinct groups: giants in closed binary systems that are spun up by tidal forces, clump stars that engulfed a stellar or substellar companion while they were on the red giant branch, and intermediate mass stars that were simply fast rotators on the main sequence.
We use high-resolution spectra of the solar twin HIP 11915 and the Sun in order to determine high-precision abundances with a precision of 0.01 dex. The abundance pattern of this solar twin is different from the Sun. In particular, we can see that the even elements are more abundant than the odd elements. For the first time, we show that the odd-even abundance pattern in a solar twin is different from the Sun. This can be explained by the contamination of a supernova from a star of 13 solar masses with subsolar metallicity. You can find more details in our published paper. Thank you.